Hello guys, welcome to this video. This is a video as part of the video series that try to help you learn how to implement the machine learning supervised method of linear regression in Python and TensorFlow. So in one of previous videos, we explained how to load the models and basically how to download and process the data sets. So in another video, we explain how to basically pre-process the data set in terms of creating the train and test data, and we have a visualization of the correlation between the variables for you to just continue and try to train your machine learning models. You can refer to the videos for information. So I prepared the code for you here in Google Collaborator. It gives you a nice environment and you can easily run the codes and prepare documentation and see the outputs. Here we are trying to basically, train the model. So we use the high-level Keras as part of the TensorFlow for creating our model. So this is a function we define, linear model. And the model here we're using the Keras sequential, the very simple one layer dense, which has only one actually output. So it's basically input shape is 1, and we have only one weight going from that one to the output. And let's just go ahead and see the Keras sequential in the TensorFlow to see what is basically the elements. So the sequentials take the layer and the name. So as simple as that. As part of the layer, these are the basic different examples. So you create the sequential model, and this is a different approach that TensorFlow is using. So I'm using a simplified approach here for you to just easily understand. So we just pick one layer, the dense layer, and we just add it to the sequential model. If you wanted to add more layers, we could simply do the same, just with a comma, another layer, another layer, another layer. So and the Keras would just stack them together. So it's very easy to use the Keras sequential models. Let's just stick to one model. So the next thing, for the linear model, we need some sort of optimizer. So for the optimizer, we use the Adam optimizer, which is one of the best optimizers it's commonly used. So let's just go to see the Adam optimizer. So for the Adam optimizer, there are different arguments. So there's a learning rate. Here we set the learning rate to 0.01. There is a beta and beta 1 and beta 2. Those are specific actually variables for the Adam optimizer, which is the exponential decay of first and second momentums. It's an epsilon. So here we take the epsilon 1 over 10 over minus 5, which is quite a small, as TensorFlow says, a small concept of numerical stability. So this is basically for some sort of computation, it's just add the epsilon, so we don't basically divide anything by 0. AMS grad is a boolean whether to apply AMS grad, actually variant of the algorithm, because there is a newer paper and a variant version of the Adam optimizer. So here for that, it put it to false. We just want to use the basic Adam optimizer and we put a name for it as Adam. So this is our optimizer, which help us to train our model with gradient descent. There are different techniques and approaches to train basically linear regression model. So it is least square, the most famous one that many people use it. So here we use the gradient descent because we want to leverage the power of deep learning GPUs and the Keras and TensorFlow for doing so, which is basically based on the mini batch stochastic gradient descent. You can read more about that. So let's just search for it. Mini batch stochastic gradient descent. As you can see, there are many different blog posts that talk about it. Toward Data Science is a nice blog that talks about this thing. So, and for the stochastic gradient descent, in our blog, in fact, we are going to cover the same topics in the future. You can just check the links below for, in fact, have an understanding of the topics and follow the same topic on our blog. So the stochastic gradient descent, as you can see, it's a method of optimization based on the loss function that we're having. And based on the stochastic gradient descent, we are going to optimize our neural network weights. So here we use a neural network with just only one weight. It's a very simple neural network. And for a model, we actually, in fact, have to compile our model using a specific loss function. So the loss function we're using is mean square error. So maybe to become familiar with mean square error, and the metric, you can go to our blog post. We just explain that thing here. So for the optimizer of the compile model, we just use the optimizer we define, and for evaluation we use mean average error and mean absolute error and mean square error for the showcasing. This loss here is the loss we're using for optimization of the training. It's simply mean square error. So here we create a model instance because we here just define the function. We need to call it. When we call it here, we have the model which we return after feeding the optimization to the compile. And this model is ready to go. So with the Keras, we can simply plot the model to see what we have inside, and we can actually save the model in a PNG. Gives us a very nice interface to work with the model. And here we are going to run it. So as you can see, the model is sequential. These are the layers we have. This is the output shape. Here it says none. It's not technically none, but it is in fact the number of the batch size. The batch size we're using for mini batch stochastic gradient descent. And these are the model summary that we just call here, which is TensorFlow printed. So there are two trainable parameters and we have no non-trainable parameters. It would be nice to print this thing to have an overall understanding of the model. So to showcase what's the difference, let's just, for education purposes, add a couple of more models again here to see how Keras is show. Oops, sorry. Yeah, it's just layered. Name layer is used twice, so we can't use the same name of the layers. Let's just put it layer 1, layer 2, and layer 3. Thank you, Keras and TensorFlow. So here, as you can see, just showcase you everything here that we have. So it just takes things different. So let's just eliminate all those things and just go again, run it. So we are going to now continue to just training the model. So for the model, we have different arguments, the number of epochs, which is the number of passes over the whole data set, each epoch. The validation split, we keep a portion of training data for unbiased validation. You can follow our blog for basically explaining the concepts. So for this is basically a portion of the training that is not used for training the model. We just try use that to test in the middle of the process, not our final test set. So this is something to want to showcase how our training is going. Verbose is some parameter that we set it to short. We want a short summary, not the whole details of the training. Callback is a powerful function defined by TensorFlow, which gives us the tool that basically we can customize, in fact, the training. So here we define our parameters, and here this is some mechanism we define as the earliest stopping. TensorFlow Keras callbacks earliest stopping. So it monitors the validation loss, and the patient's parameters is number of idle epochs. So it says if our training is not improving after this, which is 100 number of, in fact, epochs, and the improving is the minimum delta is the threshold for improving. So in fact, it says if our improving is less than this number for more than this number of epochs, just train the training, just stop the training. So it means the training doesn't make sense to continue training forever because the model is not training that much anymore. So we better stop it to save time. So this is a very important helper function in the training. So this is a prediction list, and this is a class, number of epoch logger. So we define here. So when the epoch ends, this helper class is going to, it's part of the actually callback as well. We just define a custom callback here. So it's a little bit more advanced. You can ignore it. Yeah. But for simplicity, I just explain it to you. So this callback is actually on end of each epoch is going to print these variables and values for us. The epochs, the loss, the validation loss. The loss is the loss on the training data, and this is on the basically loss on validation. The mean absolute error, the logs of validation in absolute error in the training, and again on the validation. So we just are going to demonstrate both losses and different evaluation metrics on both training and validation sets to make sure that those are consistent with each other. So the validation set, as we mentioned, is an unbiased estimator. So it's different by the statistical concept of unbiased estimator. So when we in the training process, we're going to test on the portion of the data which has not been used in the training or the final test set. So this helps us to have an understanding if really our model is training. If our training loss is going down, but our validation loss is not going down, means we're just simply overfitting. It means we're training something which is not generalizing. So let's just skip all those teeny tiny details and go ahead. And this is the log display that we use. So here is the checkpoint path. We just try to save the model, and this is the checkpoint dir. So that's the checkpoint path. So when we want to actually do the model checkpoint, so this model checkpoint actually save the models every 5 epochs, and actually every number of epochs saved. It's better as we define it here as number of logs multiplied by training input.shape. So it's basically saving frequencies. So in fact, based on the number of steps, not the number of epochs. So this is something that we just define here. As let's go search this functionality here to see what it gives us. The model checkpoint, so file path monitor where both save best only, which is save the best model only, means if our model is not training, it's not going to save it. It's a very helpful argument that we have here. Is a mode save weights only and save frequency is epoch or integer. So when we're using epoch, the model save the model after each epoch. When we're using integer, the caller save the models at the end of a batch. So which is or actually steps. As here we defined our steps, means number of epochs log, each 200 multiplied by training input.shape. So it's like after each 200 epochs, we have this number of steps, and it just saved the model. So it's simple. Let's go back to explain it again. So we have this number of samples for the whole data set, and we have this number of epochs that we want to save the model after, which means after 200 epochs, we just want to save one shot of the model. So if you multiply this number by the whole data set, means the number of steps that we have here. So after this number of the steps, which equivalent to 200 epochs, it just saved the model. And it's actually a checkpoint callback. So we just put the checkpoint path here to save the weights. And the log dir is actually, we just use the formatted time here, make sure that there is no double name. And this is the TensorFlow callback, which is the tensor board. It's very important for us. We just put the tensor board. This log dir is for our tensor board files for demonstration. And this is the last step, which does the training and save the output in the history, which the output is the loss and different things that we feed it. So here there is a model feed object, which we use the train input inside, the train labels inside, the batch size of the number of epochs you want to continue the training, the validation split, which by itself the model take 10% of the training data as the validation and the remaining 90% will train the data set. And this is the whole thing that we use as training. So this is verbose, which we make 0, and the callbacks we basically defined and explained over here. So let's just train the model. This is output from my previous file. Let's just train it again. So when we start training, here it just go ahead, and you see it's just training. We just waited for a while. This training doesn't last that much because the model is a small, and we have different mechanism of earlier stopping. So we ask the model to train or 4,000 epochs, but we may expect that to stop earlier because basically when we in fact define our earlier stopping, so you just tell the model if the model is not improving, just stop it. And the metric for that was the loss. So let's just go review the part of the earlier stopping again. So number of epochs like 200 minimum delta. So validation loss, this is basically this validation loss that is just tracking. So as you can see, it's still improving. So we expect the model to continue training. As after these 200 epochs, the improvement is less than 1/1000, which we define here as the minimum delta. So it's just still improving, so it's just stopped. So as you can see, when the model is not improving that much, just on epoch 2200, it just stopped. Let's just go ahead and we can in fact do the TensorFlow log dir here. I just commented that. You can just uncomment to show that. In fact, let's just try to see what it shows us. We're launching TensorBoard here. No, just running it. We can just simply comment it again. So as you can see, this TensorBoard gives us a very nice overview of the variables. We're tracking for the train and validation. In fact, as you can see, train is going down much faster than validation. So it's not like we're doing as good as on the training, on the validation, but it still is going down. So this is a nice demonstration of that. So let's just go ahead and take the history. So the history here is the output of our model feed, which stores the history of training, which is very important for us. For history, let's print the keys to see what we have inside the history. So inside the history, we have the loss, MAE, MSE, or for the training and for the validation. So we simply can make the MAE as the basically arrays, and for the range of the arrays that we have, we can create a pandas data frame again, and using the Seaborn, try to plot that. Basically, this plot is the same thing that TensorFlow gave us, and we just, for education purposes, try to access these history variables and try to plot them for you again, for you to understand how this is going to be demonstrated. So this is something that we have here. So for prediction, we have the model. Now we do the model predict using the object of predict on the Keras model, or basically TensorFlow model we train. And this model predict is going to take basically the test input that we created above, we flatten it and do the predictions. So we have the predictions and the correct test target values. So this test target is basically as we go up, this is the test targets of mediation value of occupied. We have the actually ground truth variables and values. So this is the test, real values, and the predictions that the model predict is the scatter plot. And we try to, in fact, draw it. As you can see, the line that the model is feeding is not that much perfect, because this model have not been trained that good, because we've used a very simple, naive one layer model here with just one weight. It's very simple, but it's still good, right? It still is just try to do something here as the model improvement. So here we are going to track the model improvement progress. This is a little bit more messy, so you can look around to see what is happening. So I basically, based on the safe checkpoints, I try to visualize how the model is in fact progressing And for each step, I just saved the model predictions with a simple line in a PNG file and try to, in the end, visualize the items. So on the blog post, you can see the visualization of the model progression. So here that was the whole basically training a model using linear regression. I hope you enjoyed it. I hope you learned things from it. I try to explain concept as much as possible. So sorry if I've been verbose. So feel free to ask questions or leave a comments if you have any. And of course, you can check the blog for a more comprehensive explanation of different concepts. And the source code is also available on the dedicated blog post for this specific video. Or in fact, this video it belongs to the blog post because the blog post been developed earlier than this. So thank you so much for watching. See you very soon with our future videos. Thanks.